In my lab, I will be examining Newton's second law by observing the change in velocity of an object falling straight down. I chose to drop a basketball and watch its motion from rest. In my observation, I found that the ball's downward speed increased over time. According to Newton's second law, we can conclude that this change in velocity is due to a non-zero net force. However, by using a computational model to predict our ball's motion, I was able to further define the total net force acting on the ball as the sum of the gravitational force acting in the negative y direction and the drag force acting in the positive y direction. When initializing my observed recording on Tracker, I first decided the orientation of my xy coordinate with the center of the ball as my origin. This way, as the ball's velocity increases, it's increasing in the negative y direction. I also aligned the y-axis with the edge of the exit door in order to account for the angle of the recording. I calibrated the scale of the film by using the basketball's diameter as my known length. In order to start tracking the position of the ball over time, I used the center of the ball at rest as my initial position. After each frame, or every 1/3 of a second, I continued to track the position of the center of the ball. Because our object in motion was blurry, I estimated the middle of the blur as my best estimate to the center of the ball. Then I used VPython to construct a computational model that could represent the ball's predicted motion given initial conditions. In my starter code, I edited the mass of the ball to an estimate of the average mass of a basketball. I set the initial position vector equal to the y-coordinate of the center of the basketball's position at rest. When determining the initial velocity of the basketball, because the object was at rest, I assumed the initial velocity was equal to 0. However, after comparing the computational model of the ball's motion with the experimental data, we see that the ball begins to drop at a faster velocity than predicted. This is most probably due to the unintentional downward pull of the ball as the student released it. In order to determine a more accurate initial velocity of the ball, I used the first data point of the ball's position after the first frame and calculated the average velocity. Next, because there is a change in velocity of the basketball, according to Newton's second law, we know that there must be a non-zero net force acting on the basketball as it's falling. When determining an appropriate measurement of the net force, I first accounted for only the gravitational force pulling down on the basketball. In order to calculate the gravitational force, I multiplied the mass of the basketball by the magnitude of the Earth's gravitational force, 9.8. I ran the while loop to calculate and track the ball's expected position after every 0.001 second, updating the ball's new velocity and position after each time interval. I compared the computational model with our observed model using a line graph. Here we can see that the computational model is a close estimate. However, there our model is predicting that the ball has traveled a greater distance than each of our observed data points. In order to get a better estimate, I went back into my Python code and included the drag force and the net force acting on the ball. Assuming that the drag force is proportional to the squared value of the basketball's velocity, I determined the proportionality constant b by observing which values of b computed a final position that was closest to my observed final position. Then I calculated the drag force acting on the system and recalculated the total force acting on the ball after each small change in time. When examining the data with the included drag force, we see that the model initially does not differ much from the model with only gravitational force. However, as time increases and the magnitude of the ball's velocity increases, the model including drag force better fits our observed data. This model also predicts that there is a terminal velocity. Because the drag force is dependent on the magnitude of the ball's velocity, we see here that the drag force acting on the ball increases over time, while the gravitational force remains constant. Thus, we can assume that there will be a point where the drag force is equal to the gravitational force, making the net force equal to 0. According to Newton's second law, if F net is equal to 0, then the change in velocity must be equal to 0, meaning our object will continue to fall but at a constant velocity. If the object was initially thrown downward, the object would travel a greater distance but would reach the same terminal velocity. I used our computational model to graphically visualize the object's terminal velocity over a greater length of time. If we drop the object at a greater height, in this computational model, the pink line shows the object's position over 2 seconds with a 0 initial velocity. The blue line shows the same object's position over time with an initial velocity of negative 1.1 meters per second. After 2 seconds, we see that the change in position over time is almost equal in both models. In conclusion, my lab demonstrates how an object falling straight down from rest has a net force equal to the gravitational force plus drag force acting on the object. Because there is a non-zero net force, the object witnesses a change in velocity until the drag force equals the gravitational force, where F net is equal to 0, and then the object will continue to move in a constant velocity.